Yeah, thank you for your introduction. And hello, everyone. I'm Joseph Kim. I'm assistant professor in computer science from Emory University. Just today, I'm talking about the AI and simulation, which is kind of broad. Uh, yeah, we'll start with an overview of modeling and simulation, or M&S, and its foundational role in the system analysis and decision making. And next, we're going to explore how the data science connects AI and simulation. And then we then look at the two kind of direction between the AI and simulation integration. So how the simulation supports AI ML by generating data and providing the controlled environment for model testing, and also how AI/ML enhanced modeling and simulation through the automation, adaptation, and intelligent behaviors. And I will illustrate this concept in user cases, including the application in epidemiology, transportation, and cybersecurity. So many real-world phenomena are manifestation of a complex system like Earth. So modeling and simulation serve as powerful computational tools for addressing the complex problem across diverse domains. And by observing a system, that we can develop a model that replicates its behavior, helping us understand how the system works and address the real-world challenges. The simulations allow us to explain the system dynamics, support education and training, and to predict the future behaviors or outcomes. Now, we can also use the simulation to develop and to test the scenarios to helping identify and potential problems or threat in advance. This enable timely planning and also the prescription of effective solution time. So today's topic, that is AI and simulation, is a core focus of my research lab. And let me briefly introduce the area we are working on. So one key update to this previous diagram is here the integration of the AI and machine learning within this modeling and simulation process. This enhancement allows us to build smarter, the more adaptive and data-driven simulation models. So in our lab, we focus two parts. One is model the system of the interest, and then also develop the tools and framework to simulate those systems. Up here, the system of interest can be very broad. The simulation can be used in the many different domains, including like biology, chemistry, and physics. But in our lab, mainly focusing on human behaviors and its surroundings from different scale, from the indoor level, across the Earth. Our lab envisioned to build this robust scientific foundation in AI and simulation for the greater good, fostering the prosperity of the nation's society while ensuring the safe and secure future for all. These are kind of themes. And main research area will be the data science using this AI and simulations. My research foundation, our lab's foundation, is geospatial database or data science, and it covers entire data cycle, including the constructed data, provided data, also consume the data in many applications. In the computer science sense, our expertise will be the spatial database, including spatial data modeling, and the computing, data mining, and analysis. We apply this to other domains such as urban data science, specifically like urban planning. And through a lot of the sensors, we can collect the mobility data, including trajectory. And then we apply this to the mobility data science and transportation. Also, we are interested in the disaster, the analysis and the management. Nowadays, we have a lot of wildfire in California, and we are recently we are working on this wildfire related simulation also analysis. And since I worked at a national lab, and especially in the National Security Division, I had a chance to work on cybersecurity, on critical infrastructure, but also non-proliferation, and try to use this AI and simulation in this domain as well. And since the privacy is a big issue and sometimes really hard to get the individual location data, and we are trying to use simulation as a tool to protect the location privacy of the individuals society. And with the census data, we know that which the individual society or the area have a less representative and maybe vulnerable. And we explore that through the tools and analysis and simulation as well. And as you know, the MR is one of the having the good school in the public health and the nursing school. So I'm also working on the project related to epidemiology, but also healthcare system. They collaborate with the public health and school of nursing. So in a nutshell, our core research area is data science using AI and simulation. As you know, data science is an interdisciplinary field, and it's really depending on domain and expertise here. To explain what my main focus is AI and simulation integration. I really want to talk about data science first. There are many definitions will be exist, and there are many different the way to explain it. But here is my interpretation. So data science is data plus science and something, right? ARPA. And I think these are three main component or ingredient, if you will, the data and scientific methods and very different tools. So here the data is the research or the interest that we are focused on, but the scientific method will be the process, very given the rigorous process that we have to adhere to. And then there are many different techniques. It could be, the mathematics, the statistics tools, and the computer science tools as well. And eventually, using these tools, we want to obtain these different goals, understand, analyze, and predict behaviors and the phenomena, and eventually aid to make a decision. And here, what we do we usually the answer the question during the presentation, or okay? I'm sorry. I thought it's a question, but it's not actually chat. Okay. Here, I argue that we can actually use the AI and simulation in this figure. I mean, it's part of this data science. I will show that in a minute. And
Dr. Kim, yeah, it's up to you. You can just answer the questions during the presentation, or maybe we can hold at the end of the presentation. It's up to you.
Okay, thank you.
If
there's a
particular question is directly related to the current slide, maybe okay, it's completely up to you.
Okay, thank you. All right. Yeah, so back to here. In general, the data science, we argue that there are a lot of tools like data processing and the computers, using the programs and or called the data engineering. And there are different tools, but here my focus is more on the AI as the techniques and also modeling and simulation, part of the technique, but also the process. And the reason why I try to combine that in this data science kind of platform, because it's more about what kind of tasks we are doing. Here we can categorize data analysis into four groups. So one is descriptive analytics. It's really focusing on when we have the data, we just focus on what happened in the past. So describe the data using the descriptive, the statistics and visualization and so on. But it really cannot answer the why question, why something happened, and correlation is not really causality. So there's another field focusing on, why something happened. So we try to understand the causality. And this analysis is called the diagnostic analytics. It's a little more difficult, but it's more valuable. And the machine learning and AI in general, really popular, the task will be the predictive analytics. So it's focusing on what will happen. And the eventually, what we need is, if something happened like the pandemic, then can we reduce or minimize the damage from this catastrophic events? So then how we can actually make it happen? This is called the prescriptive analytics. And from the raw data and make the information, and we gain the hindsight, eventually we get an insight and the foresight through this process. And our lab the work on each of this, but in the AI and simulation, using this AI and simulation tools. Before, I mean, my talk will be somehow the position in this different kind of lab analytics, but also there's another part, the modeling and simulation. So again, in this talk, we are trying to talk about the conversion or integration of the modeling and simulation and AI. And then one of the way to integrate is how the AI actually integrate or help the modeling and simulation process. So here we have the problem entity or system, and the first step will be from the analysis of observe the system, we build some conceptual model. And then, so in this talk, we're only focusing on computerized simulation, meaning we have to implement as a computerized model. And eventually, we run the simulation and the evaluation and experiment and compare with the actual system. So these are the process. And this is not just single kind of process. It's iterative process. We need to validate our conceptual models or verify that and so on and so forth. So I'm trying to explain how we can integrate the AI simulation in these two themes. The first part will be how we can actually model the conceptual model first. I will just skip the descriptive analytics in this talk, although it's very interesting the area, and but yeah, I will focus mainly on the three aspects in this talk. Let's say you have like the AI and machine learning tools that either through the causal inference, or you try to find causality, or you want to predict something. Yeah, there are many techniques, and one of the problem is like especially social science, you do not really have the data. I mean, when I say the data, how do you know whether people actually behave? What is their motivation? Without a survey, which is very expensive, there's no way actually get those ground truth data. So the simulation can really important role here. So we create a ground truth simulator, and it create the artificial socially plausible simulation. It will generate a bunch of the data for the researchers, and who have no idea how they actually implement this world, only get this data and apply it in their own method to explain this world or predict phenomena and prescribe if there's any the event. at the end, we compare what would the best kind of method they compare with the ground truth simulator. So here, one of the recent our the publication this kind of theme is in silico human mobility data science. So in silico means like it's controlled environment. We have a lab environment so that we know what really happened and whether this method or tools are really work effectively and so on and so forth. These are maybe a five the main kind of the component in this the cycle. So first step will be the build the model, modeling part. And the one of the way actually traditionally we represent our conceptual model in the language like natural language or the this kind of diagram so that yeah, very common, right? Like object-oriented programming type of the diagram so that you know how to implement this simulation. Of course, this is agent-based, but you can apply to the discrete and simulation as well. So you have this kind of concept, but nowadays we can actually use AI like LLM to generate those the conceptual the model as well. So once we have this, build this model, we run the simulation or implement it, and main focus of this the simulation is human behavior and also their mobility. And on the left-hand side, we have a massive behavior micro simulation, and it will generate the simulation of individual plate where they go, and they only focusing on only the behavior part, the motivation. But the just imagine if you wanna, let's say, go to work, then you have to decide what is your route, what kind of the mobility, the modality you're gonna use. So, and these are itself a very complicated ones. So we have a separate different the massive traffic micro simulation, and then it's the back and forth, and we try to co-simulate this. And these are part of the output or and I can explain maybe with some visualization. Once we have this simulation and generate a bunch of data, and in this diagram, this two figure, it shows the comparison of the location-based social network or LBSN, between the real data and simulated data. The left-hand side is a koala, the data, which is a business date, literally business date, but only have a 69 users and 710 check-in a day. But now we can, through those data, we generate these check-in data, and really not only it's ground truth, but also it has the dynamic social network and so on and so forth. So we generate the different area, including the synthetic map and the real map, Atlanta, so on. Now, once we have this ground truth data, then we can do this in silico, the human mobility data science. So mimicking like in real world, we do not have actually the entire ground truth data. We maybe have a sample. It could be a very rare, just few sample, but we still try to split as a test and train data set and build a model. You can apply the different kind of method, including the visual analytics and prescriptive analytics. Eventually, you can compare with this ground truth, similar like validation set. So once we have this process, we can apply the many domain using this data. In the left-hand side, you can see that we apply this mobility data to the predict, in this case, the progression of epidemics, and we can apply different intervention like vaccinations and the place closure and so on. And although we can just keep using this data, but also we can improve it. So to do that, we first developed our metrics, and then we compare the mobility pattern between the simulated data and also real world data. In this case, this is a travel survey data, literally survey where they go and how often they travel, for instance. So in this pattern, you see how much they travel from home to work or home to the school and so on and so forth. And we try to compare with the simulated data and then find the normal patterns, understand the limitations of the model. Eventually, through this, we can develop a new hypothesis and go back to the original, the first step, which is model building. And the one of the ongoing research areas will be this: how make this simulation realistic. So this research started from when I was in the Oak Ridge National Laboratory. And there are many components, but there's two crucial components to argue that our simulation is really realistic or accurate. We still rely on our observation, and the two part, one is modeling and the other is data prediction. So whether we have sufficiently captured the data, behavior interaction, the large population heterogeneous actors. And once we have that model part, and can we actually map their behavior in the real world, and so that we can run the realistic simulation to aid the decision making. And we have to actually integrate the many components to make more realistic simulations. So like places and social network and the individual characteristics, their activities and their mobility and so on. So it will manifest over time in a different scale, like the daily or weekly and seasonal. And it's compared to the black box ML model. This kind of simulation can provide some explainability. To do that, we need real data, right? So here we have different kind of data sources, OSN, OpenStreetMaps, or you have ESA data structures, census, and the maps and trajectories. Through this data, we can't just directly run the simulation, so we need some process and imputation and so on. So we had to develop different kind of tools, generate the transportation network, for instance. And also the point of interest. In this process, we actually had to use the AI or machine learning tools as well. So this is a part of the modeling simulation, but we are heavily relying on statistics or the ML. And once we do that, we generate those data that can be at the input of the simulation. So including the synthetic population or popularity and origin destination metrics and so on. So again, when they use this real data, sometimes, yeah, the real data is good. We have a bunch of sources like satellite imagery, 3D point cloud, street view, and so on. But sometimes coverage, it's not really covered the entire Earth, or maybe the indoor is not covered. And also the low quality is not really update, every the month, maybe depending on type of the data. And that's why the data would be very useful, like synthetic city data. Like you can apply that. We can use that in the many application, urban simulation, social simulation that I just explained. Also the urban test bed. Like one of the example will be I think Professor Kwan actually, I believe, the working this area, like a self-driving cars and transportation. You can use it as a color, which is an open source simulator for automatic autonomous driving the part. Yes, instead of using the real data, maybe you can just, have, by the way, I'm not a part of this project, the member, but Yeah, these are all the 3D rendering in the simulation, but it's not real data. But you can use this platform to actually train the AI model. So I think that's why the generate this synthetic data itself is a really important the part. And the other aspect is how, our agents, I mean, the traditional, the agent-based model is relying on the handcrafted model. But nowadays we have this LLM, and our ongoing research areas, can we actually use LLM to make a more, when we have the interaction between the agent, I mean human, can we have a more realistic the social simulation? The right hand side, I think many of you already know that this is the generative the agent developed by the Park Chun-sung, I think from the Stanford University. But the problem with this approach is very expensive. So the one of the researcher I'm working on is, can we combine? I mean, can we scale this up, and so that similar, have the similar kind of effect that we had in the large scale simulation. So we talked about the how make our environment more realistic, or also the behavioral part. That way we can combine this AI and simulation. And here, this is another the domain that we can use this simulation to as a data generator. So this is work that that I've done in the PNNL and to collaborate with them. Here, the 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 national labs, including the PNNL, ORNL, they're the DOE lab, the Department of Energy, and they're really interested in the energy in general, and also security. And just imagine we have different kind of the electric sources like fossil fuel or the renewable energies and so on and so forth, and maybe even from the the community, like solar panels. So then it literally transmits the data, not data, sorry, the electricity through the line and distribute them. And those are all the happen through, I mean, remotely, because we have this control center, and then we try to the control all the facility computer. Then the problem is, what if there's some attack? Then can we actually build any model to detect those, the cyber attacks? We cannot really, I mean, the first of all, do we have those data? I mean, if you have the data, I think they have, of course, they have data, but very few. And we do not want to have those the attack in the power grid, right? So the idea is, can we build this simulation testbed for the cybersecurity? And here, left-hand side, we have a control center, and the right-hand side, we have a microgrid. And there are many components, in the electric engineering part. And this SS means the substations. And just imagine there's some attacker can adhere their communication, also the alter their messages, right? We can create those scenarios. In this case, yeah, it's called a man-in-the-middle attack. So it could be internal actually, workers who work here can actually the alter those the certain, in this case, close switches or change the voltage in the inverter and so on and so forth. To implement this, we have developed this co-simulation framework. So because in the left-hand side, we have a grid lab focusing on the electrical engineering simulation. And then right-hand side, we have the NF3 network simulator. And then we use this Helix to combine these two and you know the and all including the application layer, the network. So they use a specific kind of the layer called the DMP3. I mean, one of the protocol will be the DMP3. And we try to use those information. Of course, these are not real the creed, but IEEE provide this different type of the test feed or both system we can play with. So these are the one of the system we use in the paper, and it will generate those application level the data like the MP3, and really you can read the packets and manipulate. Attacker can manipulate that using this data. Now we have the data, right? So if you have those attacks, then how the voltages will change in a real degree system, right? You can generate those the scenarios and then the text. Then we can use this data to train the machine learning model. So so far I talked about how we can model different domain. And then now I'll move on to the prediction part. So the more focusing on simulation aspect, the one of domain that I worked on is the epidemiology. So on top of this social simulation, I try to add one more layer, like influenza virus or the COVID, something like that. And the left-hand side, you can see, these dots are agents, and yellow agent means susceptible to the flu or epidemic. Then exposed, infectious, and the recover. There are 4 different stages. And on the right-hand side, you can see the social network, how we just analyze how the disease spread through the network. Also, you can see number of infection over time, and how the social network will change when we have this the epidemic spread. All right. So using this simulation, we can actually predict the future. In this case, here as I said, there are 4 different states, and one curve represent the one simulation. But yeah, we change some like random seed and so on, and we can have a bunch of different the simulation output. And once we have enough sufficient the number of the simulation, we will have this very smooth kind of curve right now, and we can use these curve to predict um, the progression of this disease, for instance. This is a one way using just purely the data. The modeling simulation using the handcrafted the model, but also we can do a data-driven mobility model. During the pandemic, we could use this the SafeGraph data for free, and it provides us the mobility pattern. It's not really trajectory due to the privacy issue. They have a visit patterns for each the census block group, and we know that where they actually visit. And what we are trying to do is extract the patterns and their behavior from directly from the data. And then we try to find the common pattern, like for instance, CBG1 and CBG2, they have a kind of similar pattern, visit patterns, and 3 and 4 have a similar. And the idea is how can we extract that without the developing model from manually. And for instance, CVG, there are for different CVGs there, and it just shows kind of heat map, and we can uh, cluster the common the part, like I mean, very common the similar kind of topics. Then in this paper, we use the LDA to kind of as a topping model to model the mobility pattern, and we using this data again, we did a simulation. What if we know that how the people to behave and the move around, then can we put the flu or this case the COVID uh, uh, the layer so that we can predict how the those are spread depending on the different the topics and number of topics and the population. So this is yeah, one of the approach, and there also another approach. Let's say we have different types of models, simulation models, and they predict different. Yeah, as you can see, during the pandemic, we had tons of the prediction models, which is also in the archive in the CDC. And the idea is, can we actually build the ensemble model using the AI and ML? So these are also one of the way they combine this AI and machine learning, AI and the simulation. So in this case, uh, we can do the simply stacking or using the ML model to make this the example model as well. And this is just visualization of those example the models and individual ones. All right. And next one will be the ultimately if you have this the result, but the what we want is actually change the future, right? So now we're gonna talk about the prescriptive analytics part, which is in the the experimentation in the modeling and simulation process. So once we have simulation, then we want to do a lot of experimentation here. To do that, we have to develop some tools. Like if we want to do the what if analysis, then we need to actually introduce those what if intervention in the simulation. And also, if you have different the policies and so on, then the if you have a lot of policies, then you have to run the multiple simulation to optimize the many different aspects. And the idea is how we can actually streamline experimentation. And well, the first step will be to inject this intervention in the running simulation. So these are the tools we can use that. So here in this case, original, let's say the simulation, but we want to literally inject different behavior during running the simulation. And I developed this tool. So we have the model and simulator. We just run the first run and then get the result and then examine that, okay, can we do better? So we identify, we have multiple intervention and we create this predicate and then inspect the simulator in the runtime and then identify the point that we will inject. And then we have a new branch and using this new branch, we do one more the analysis and we're repeating this process. Eventually we want to minimize, let's say the spread or damage from the pandemic. This is also more like the expert in the loop, meaning the human in the loop. Human have to actually who has an expert is to set up the point and what is the current status, and maybe we can, this is a kind of good timing to start, an intervention. So here using the patterns of life simulation, which is a social sim that I developed, and we can integrate that with um, the SEIR model. And here the experiment including the interventions scenarios including the PPE, like wearing the mask or social distancing. This kind of setup. Once we have that, we introduce, yeah, this is original simulation, like blue curves. If there's no intervention, then this is gonna be new cases over time. But if we introduce like wearing a mask or social distancing order, then it will flat the curve and so on and so forth. So, but these are not really optimized, and this is more like human in the loop to make more the uh, to optimize. We actually need to rely on the AI ML model as well. So the one of yeah, during this pandemic, and I think 2020, there's the workshop, KDD workshop called the Challenge on Mobility Intervention for Epidemics, and apply. I mean, in this the challenges, the objective was to minimize number of the people get, I mean, number of infection, and also the minimize number of interventions. Meaning, if you have intervention, of course, you can minimize the if you have a lot of the intervention, then you can actually reduce infection, but it's really costly. So these are the competing objectives. And we had to consider this to a competing objective and introduce this for different interventions, confinement, out quarantine, isolation, and hospitalized, which has a different kind of cost. And this scenario, we had the 10,000 agents. And so imagine if you just select some of this population and introduce this intervention, there are so many different the cases. So the number of combination of these interventions increase astronomically, and that's why we cannot just use ML model and still need to rely on the experts' knowledge. So here, what is proposed was expert in the loop. So develop heuristic or certain rules, and we optimize certain parameter and then evaluate our pattern whether it's really reduced. I mean, there's a cost function and whether it's really did well or not, and then we readjust that and then you apply the different kind of method, including reinforcement learning or genetic algorithm programming, so on and so forth. So we are not sure which one will be the best, but the idea is still we can rely on the expert knowledge to the expedite this optimization process, and still the modeling and simulation is as a ground to work for prescriptive analytics, and we can apply that also to the different domain like transportation. I think I presented this long time ago in the Oxia as well. So here we have Uber, let's say app, and these are the user's point of view. These are more the driver's point of view. What the both are need is when the users they call the Uber, then the without the minimized waiting time, but also for the drivers, they maximize the income. And then, but if they don't know how people will behave, like including the drivers, yeah, they will go to the same place like this one, like herd. We call it herding. This is at JFK, the airport. And these are the problem setting. Let's say you have a New York, you are in the New York City, and you the hailing the taxi. Then authority will assign the nearest car, and the driver will pick up and drive to their destination. After drop off, I have to decide, where they go, and we use the New York City data to analyze their patterns, the pickup and drop off, and here we can use a simulation as well. this is the entire kind of architecture here. So we have the real-time data, right? String the data, and then using this historical data, we can build the prediction model, and then each agent have their own the strategy, and also using this knowledge to maximize the income. So yeah, the left-hand side, just a visualization of the comparison between these two approach. One is the baseline approach, and the right one is our approach. In our approach, if you look at here, the red ones are weighting the passengers, and it's reduced much significantly. The white one is the taxis here. So here, the due to the time limitation, we'll just skip the detailed explanation. But the one of the important aspect will be the analyze spatial temporal pattern. This diagram is a heat map of the monthly pattern, and here the row are the spatial the patterns, and these columns the temporal pattern, so that this can be the daily pattern, or this can be the weekly pattern. So in this work, this pattern considered as a latent feature. So there are many approach, and other teams also use a different approach. But in this work, I use the non-negative matrix factorization to decompose this component and identify what would be the spatial features and the temporal features. And for instance, these are when we have 6 different spatial features, then these are very we extracted the data, and these are common feature. And for instance, it has two different the aspect. One is the spatial and the temporal. These are pure, the spatial aspect, how that resources are spread in space. And one of the latent feature, if you look at here, has a very concentrated in one place, and we noticed that this is the Penn Station in New York City, and because there are many things called happening here, so it just manifests as a feature as well. And then the idea is, can we actually predict using this special component, knowing that this temporal aspect as well. Okay. Yeah, I think I show the different, many different the concepts and the works, but here we have tactical messages. So to integrate this data science and AI and the simulation, I use data science as a platform to integrate these tools. And then the modeling and simulation can be the source of the data for AI model training, but also validation. And also AI can enhance the simulation process. These are not an exhaustive list, but we can identify this 3 different parts, like model specification. So you either using the LLM or AI assistant to build the model, or data-driven feature extraction for both the agent and environment. Or we can use the AI/ML to directly build behavior model, like LLM, and also to evaluate this simulations. We need a lot of process, including the model calibration, validation, and sensitive analysis. And this process also need some optimization process. So we that way we can use AI to the simulation as well. So with this combination, uh, we get a lot of benefits. For instance, increase efficiency to automate this task uh, of the simulation workflow and improve the accuracy. It's more realistic and precise simulation when we use AI model. And also the better decision making, especially when we directly use ML in the decision making process. So back to the original, first diagram. What is data science? Here the interest will be the different data sources, including public health, gesture, the cybersecurity, and I'm using the simulation as a process. And AI/ML is actually part of these tools. LM, or if we want to scale this up, then we also consider the distributed computing. And eventually, we want to achieve the different the goals here. So that's it for this talk. Thank you for your attention. If you have any questions, feel free to ask. I think you're muted. I cannot really hear you.
Okay. Yeah, that happens always. I'd like to stop recording before we get questions. Let me stop.